December 16th, 1944, Elsenborn Ridge, Belgium, 0820 hours. The frozen air of the Ardennes carried the dull, rhythmic thunder of artillery, an old, terrible music that had echoed across Europe for half a decade. Snow, packed hard by the tread of vehicles and boots, vibrated with each concussion. Through the drifting mist, Oberst Wilhelm Osterhold of the 12th Volksgrenadier Division stood on a rise beside his command post, binoculars pressed to his face, his breath crystallizing in the cold. Below him, his regiment's batteries stretched across the frostbitten hills, firing in disciplined rhythm. 90 minutes of calculated destruction. 90 minutes of preparation for what the German High Command believed would be the final decisive offensive in the West, the Ardennes counterattack, Hitler's last gamble. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Osterhold had commanded artillery since the invasion of Poland. He knew how to prepare a battlefield. His staff officers had laid out precise firing tables the night before, coordinates, fuse timings, charge increments, all refined by years of experience. Impact fuses for bunkers, delayed fuses for penetration, time fuses for airbursts over infantry. Each round served a purpose in the great orchestration of fire. He'd seen it work before at Smolensk, at Kursk, at Caen. War was an equation of trajectories and timings, and Osterhold had long since learned how to balance it. He was confident that morning. His gunners were veterans of a dozen campaigns, men hardened by retreat and desperation, but still lethal behind their 105mm and 150mm guns. Across the valley, the American lines at Elsenborn Ridge looked deceptively quiet, the enemy hidden behind their dugouts and snow-camouflaged emplacements. Soon, the infantry would move Volksgrenadiers advancing through the shattered woods to seize the high ground. The artillery's role was simple: crush, disorient, and pave the way. What Osterhold couldn't know, what no German officer could have imagined, was that this morning, the fundamental laws of artillery warfare were about to change. At 0847 hours, his forward observer radioed a terse warning. "Counter-battery fire incoming." Osterhold barely reacted. Standard procedure. The Americans always replied after enough muzzle flashes gave away positions. He expected a few ranging shots, perhaps a brief duel. His men knew what to do: keep firing, move after 5 salvos, dig in. Artillerymen survived by habit and rhythm. But the first incoming shells behaved in a way that made no sense. They did not impact the frozen ground around the gun pits. There was no dull thud of earth erupting, no geyser of snow and splinters. Instead, the shells detonated in the air a few meters above the emplacements, with a strange, flat burst that sounded different from anything Osterhold had ever heard. A moment later came the scream of fragments descending at near supersonic speed, slicing through the open gun positions with surgical precision. In the span of seconds, his lead battery vanished into a storm of metallic hail. Gun crews standing by their breeches fell where they stood, their winter smocks shredded by downward-travelling shrapnel. Horses and ammunition trucks were shredded alike. Those who dove for cover were killed just as efficiently as the deadly steel rained from directly overhead. Osterhold lowered his binoculars in disbelief. There had been no warning impact, no ricochet, no misfire, just instantaneous, calculated annihilation. "Verdammt," he muttered, snapping his field phone to his ear. "Battery 1, report." There was only static. He turned to his staff. "They're using proximity fuses," one lieutenant whispered, though even he didn't fully understand the term. It was something out of rumour, a fuse that could sense its distance from the ground, a weapon that exploded when it wanted to, not when it struck something solid. Osterhold dismissed it at first. Such precision was impossible in field conditions. Artillery was art guided by mathematics and weather, not science fiction. But then the second salvo came. The next shells descended like clockwork, each bursting almost exactly 30 feet above the next battery. Again, the air seemed to crack open white flashes suspended in the mist, and fragments screamed downward in perfect dispersion cones. The second battery commander ordered his crews into their slit trenches, the way every artilleryman was trained to survive counterfire. The men obeyed, throwing themselves into shallow dugouts just before the next wave hit. It didn't matter. The proximity-fused shells detonated directly above the trenches, the fragments striking at angles designed by no human hand present to kill men even in cover. The trenches became coffins. Osterhold watched helplessly as movement ceased across the slope. Within 3 minutes, 3 of his gun positions had been wiped off the map. The silence that followed was worse than the noise. To the Americans on the ridge, the innovation at work was not new, though its existence was guarded more closely than the Manhattan Project. It was the VT, variable time proximity fuse, a technological leap years ahead of anything Germany possessed. Inside each 155mm shell was a miniature radar system, an electronic brain that emitted radio waves and measured their reflection from the ground below. When the reflected signal reached a specific strength, indicating a set distance, usually around 30 feet, the fuse detonated. No stopwatch, no guesswork, no weather correction. Every round became an intelligent airburst, calibrated to perfection regardless of terrain or angle. The fuse had first been tested in anti-aircraft shells against V-1 flying bombs. Its success rate had stunned the Allies. But its use on ground targets was restricted until December 1944, when intelligence confirmed the German offensive through the Ardennes. At Elsenborn Ridge, for the first time in history, proximity fuses were unleashed in massed field artillery fire. The results were immediate and catastrophic. By 0850 hours, the 12th Volksgrenadier Division's artillery regiment was no longer combat effective. Gun barrels lay twisted, ammunition burned in neat rows, and the snow was stippled with the dark signatures of fallen men. Osterhold's surviving staff officers tried to re-establish communication, but the field lines were cut or buried. The regiment's fire support for the infantry assault, the critical opening move of the offensive, had been annihilated before it could even shift targets. Osterhold himself crouched behind the remnants of his command vehicle, ears ringing. The world seemed to have tilted out of logic. He had faced Soviet Katyushas, American airstrikes, British counter-battery radar, but nothing that could destroy with mathematical exactness from the sky. He whispered to his adjutant, "They know where we are, exactly where we are, even our depth." But his adjutant shook his head. "It's not the aim, Herr Oberst. It's the fuse." The Oberst didn't respond. His mind raced, grasping at artillery tables, fuse types, wind corrections, every calculation that had once governed survival. None of it applied anymore. The enemy shells were thinking for themselves. As the smoke thinned, American spotter aircraft circled above, directing fire with impunity. Every time a surviving German crew tried to reman a gun, another perfectly timed airburst erased them. The rhythm of war had changed. Man and machine were no longer equal partners in destruction. Technology had stepped beyond comprehension. By 0900 hours, Osterhold ordered the remnants of his regiment to withdraw what few could still move. The artillery that had once been his pride was reduced to silent wrecks scattered across the snow. For the rest of that day, German infantry advancing toward Elsenborn Ridge did so without artillery cover, walking unknowingly into interlocking fields of American fire. The Battle of the Bulge would rage for weeks, but the outcome, at least on this sector, was decided in that half hour of unimaginable precision. Later, survivors would speak of shells that knew where to explode, of invisible devices that sensed life and death. Some called it witchcraft, others, divine retribution. But historians would mark that morning at Elsenborn Ridge as the dawn of a new era, the moment when warfare crossed from the mechanical age into the electronic one. And as Oberst Wilhelm Osterhold looked across the field of shattered guns and frozen men, he understood one thing with cold certainty. The art of war he had mastered for 5 years had just become obsolete. The weapon devastating German artillery positions was designated the VT fuse, officially the variable time fuse, though internally the American military knew it as the proximity fuse. The designation variable time was deliberate misdirection designed to make captured examples appear to be merely improved mechanical time fuses rather than the revolutionary radio frequency devices they actually were. Development had begun in 1940 at the request of the US Navy, desperate for more effective anti-aircraft ammunition. Traditional anti-aircraft fire required calculating a shell's time of flight, setting a mechanical fuse to detonate at the predicted altitude, and hoping the aircraft would still be there when the shell arrived. Hit rates were abysmal, typically less than 1% even with radar fire control. The proximity fuse solved this by transforming each shell into an autonomous sensor. A miniaturized radio transmitter inside the fuse emitted a continuous signal. When the shell approached within lethal distance of a target, the reflected signal triggered detonation. The shell, in effect, detonated itself at the optimal moment without any human calculation required. The technical challenges seemed insurmountable. The device had to fit inside a standard artillery shell, survive acceleration forces exceeding 20,000 Gs when fired, operate reliably across temperature ranges from -60 to +150 degrees Fahrenheit, function while spinning at 500 revolutions per second, draw power from a battery activated by firing acceleration, transmit and receive radio signals while traveling at 2,000 feet per second, discriminate between ground and aerial targets, and cost little enough to be manufactured by the millions as expendable munitions. The National Defense Research Committee assembled teams from Bell Laboratories, the Carnegie Institution, Johns Hopkins Applied Physics Laboratory, and dozens of other institutions. What they created was an engineering miracle. A rugged 5-tube radio transmitter receiver, small enough to fit in a shell nose, powered by a battery activated by firing setback forces, employing vacuum tubes designed to survive accelerations that would crush conventional electronics. By 1943, proximity fuses were in combat use with the U.S. Navy, devastating Japanese air attacks. But use on land remained absolutely forbidden. The security restrictions were draconian. Fuses could only be employed over water where duds couldn't be recovered by the enemy. The British, despite being close allies, weren't fully briefed on the technology until 1944. Soviet requests for the fuses were denied outright despite the alliance. The calculations were brutal. If Germany obtained and reverse-engineered the proximity fuse, their air defences would become catastrophically effective against Allied bombing raids. Every shell fired by German anti-aircraft batteries would become an autonomous hunter. The strategic bombing campaign might become unsustainable. Worse, proximity-fused artillery shells fired by German guns could devastate Allied forces attempting the invasion of Europe. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. General Dwight Eisenhower personally authorized the first ground use of VT fuses during the Battle of the Bulge. The calculation was simple. German forces were in full offensive, recovery of duds from contested territory was unlikely, and Allied forces desperately needed every advantage to contain the breakthrough. On December 16, 1944, the same day the German offensive began, American artillery received authorization to employ proximity fuses in ground combat. German artillery crews first encountered proximity fuses without understanding what they faced. The initial assumption was that American time fuses had improved, perhaps through better quality control or more precise manufacturing. This explained nothing. Lieutenant Hans Becker, commanding a battery of 105 mm howitzers in the 2nd Panzer Division, recorded in his diary on December 19th, American counter-battery fire today demonstrated unusual precision. Shells burst consistently at identical heights above our positions. Our casualties were severe despite proper defensive procedures. The explosions occur too high for ground cover to provide protection, yet too consistently to be conventional time fuses. Requested technical intelligence assessment. That technical intelligence would never arrive with satisfactory answers. German captured munitions experts who recovered unexploded VT rounds found the interior mechanisms baffling. The miniature radio components seemed impossibly sophisticated. Initial reports speculated the devices might be remotely triggered by American radar installations, though this theory failed to explain how hundreds of shells could be individually controlled simultaneously. What German gunners experienced was systematically consistent lethality. Every proximity-fuzzed shell detonated at optimal burst height, typically 20 to 40 feet depending on shell caliber and target type. The Mark 53 fuse used in 105mm shells was set to function at approximately 30 feet above ground. The Mark 45 for 155mm rounds functioned at 35 feet. These weren't approximations or averages. Every single shell detonated at the programmed height with mechanical reliability. The psychological impact was immediate and profound. German artillery crews had developed elaborate protocols for surviving counter-battery fire based on 5 years of combat experience. These protocols became useless. Taking cover in slit trenches provided no protection. Dispersing from the guns after firing offered minimal benefit because the fragments rained down across wide areas. Even the timing of cover taking became problematic. There was no ground impact to signal when to take cover. Shells simply exploded overhead without warning. Hauptmann Friedrich Weber, a battery commander in the 277th Volksgrenadier Division, reported to his regimental commander on December 23rd, "Our casualties from American counter-battery fire exceed anything experienced on the Eastern Front." Soviet artillery, though tremendous in volume, could be survived through proper technique. American fire, though less voluminous, produces casualties regardless of protective measures. Recommend immediate technical investigation and tactical countermeasures. No effective countermeasures existed. The fragments from an airburst shell spread in a roughly conical pattern downward, covering an area far larger than any ground burst. A single 105mm proximity-fused shell created a lethal fragment pattern approximately 100 feet in diameter. A 155mm shell's lethal radius exceeded 150 feet. Crews dispersed from their guns by 50 or 75 feet, standard procedure against conventional fire, remained well within the kill zone. The lethality of proximity fuses derived from pure physics and geometry. When an artillery shell detonates on ground impact, roughly half its fragments are absorbed by the ground itself or thrown skyward at angles too steep to be effective. The lethal fragment pattern is asymmetrical, concentrated in the direction of shell approach, limited by terrain masking and ground absorption. An optimally timed airburst eliminates these inefficiencies. Detonating 30 feet above ground, fragments radiate outward and downward in a uniform pattern. No fragments are wasted into the ground. The downward angle ensures fragments strike targets from above, defeating foxholes, slit trenches, and hull-down positions. The consistent burst height creates predictable, overlapping lethal patterns, allowing for precise fire planning. American ordnance specialists had calculated the optimal burst heights through exhaustive testing at Aberdeen Proving Ground. For anti-personnel use against troops in the open, 25 to 30 feet provided maximum effectiveness. Against troops in foxholes, 20 to 25 feet sent fragments at angles steep enough to penetrate vertical cover. Against vehicles, 35 to 40 feet created fragment patterns that struck engine decks and crew positions from above. The Mark 53 proximity fuse, standard for 105mm howitzer ammunition, operated by transmitting a radio signal at approximately 200 MHz. The reflected signal bounced back from the ground, increased in strength as the shell descended. When the signal strength reached a predetermined threshold, corresponding to an altitude of approximately 30 feet, the fuse fired. The entire process, from signal transmission to detonation command, occurred in microseconds. The elegance was in the simplicity. The fuse didn't calculate altitude or measure distance. It simply responded to reflected signal strength, a measurement automatically affected by proximity to the ground. The physics were self-correcting. If a shell approached at a steep angle, it descended faster toward the ground, reaching triggering distance more quickly. If approaching at a shallow angle, it traveled longer before triggering. The result was consistent burst height, regardless of firing trajectory. German technical intelligence, analyzing captured fuses, struggled to comprehend the engineering. A functioning radio transmitter receiver inside an artillery shell violated everything they understood about electronics and shock resistance. German radio tubes, even in carefully packaged ground equipment, were fragile components requiring gentle handling. The concept of radio tubes surviving 20,000 G acceleration seemed thermodynamically impossible. The reality was equally revolutionary manufacturing as much as design. American industry produced over 22 million proximity phases during the war, each one a miniature radio station, each one manufactured to exacting tolerances, ensuring reliable function. The production facilities at Eastman Kodak, Philco, Sylvania, and dozens of other contractors had transformed proximity fuse manufacture into assembly line production. Quality control was absolute. Failure rates in combat use were less than 2%. German artillery doctrine in late 1944 remained fundamentally sound in concept. Batteries fired from prepared positions, displaced after firing to avoid counter-battery response, used flash and sound ranging to locate enemy guns, employed smoke and deception to mask their own locations, and maintained communications security to prevent radio direction finding. These techniques, refined through years of combat, became marginally effective against proximity-phased counter-battery fire. The problem was mathematical. Even if a battery displaced after firing, it had to move to another prepared position. These positions, once targeted, could be engaged with proximity-phased shells that didn't require perfect accuracy to achieve effects. A conventional high-explosive shell had to detonate within approximately 10 yards of a gun position to reliably damage or destroy the weapon. Proximity-phased shells created lethal fragment patterns 50 yards in radius. This 5x expansion of effective radius translated into a 25x increase in effective area. A battery position that might survive repeated bombardment by conventional shells could be devastated by a single proximity-phased fire mission. American counter-battery doctrine evolved to exploit the proximity fuse's characteristics. Rather than attempting to destroy German guns through direct hits, American fire direction centers planned for suppression and crew casualties. A battery engaged with proximity-phased shells might retain operational weapons but lose the crews to operate them. Gun tubes could be replaced relatively easily. Trained gun crews, especially in late-war German forces, could not. The 2nd Infantry Division, defending Elsenborn Ridge during the Battle of the Bulge, demonstrated the devastating effectiveness of proximity-phased counter-battery fire. German artillery supporting the 12th SS Panzer Division's assault was located through radar and flash ranging. American 155mm battalions engaged with proximity-phased ammunition. After 30 minutes of intermittent fire, German artillery support for the assault had been reduced by an estimated 70%, not through destruction of weapons, but through crew casualties that made the guns inoperable. Oberst Wilhelm, commanding the artillery of the 12th SS Panzer Division, reported on December 18th. American counter-battery methods produce casualties that make continued operations difficult. Guns remain operational, but crews are depleted. Replacements from infantry units lack training. Recommend immediate investigation of American fuzzing methods and development of effective countermeasures. The countermeasures didn't exist. German artillery could attempt to increase dispersion, spreading batteries over wider areas to reduce casualties from individual salvos. This degraded coordination and made battery control more difficult. They could improve camouflage and concealment to avoid detection. American radar and aerial observation made this marginally effective at best. They could accelerate displacement after firing. This reduced sustained fire rates and complicated fire missions. The Battle of the Bulge provided the proving ground for proximity fuses in sustained ground combat. German forces, concentrated for their offensive, presented targets that American artillery engaged with systematic efficiency. On December 17th, elements of the 1st SS Panzer Division attempted to force the Elsenborn Ridge defended by the 2nd and 99th Infantry Divisions. The American artillery, including the 196th, 955th, and 997th Field Artillery Battalions, had been allocated proximity fuses for the first time. The fire direction centers planned missions assuming airburst effects, concentrating fire for suppression rather than destruction. The results were catastrophic for German assault forces. Infantry advancing in company formations were engaged with proximity-fused fire. The shells, bursting 25 feet overhead, created nearly perfect kill zones. Men who dropped prone, standard response to artillery, were struck by fragments travelling downward. The fragment density was such that individual foxholes provided minimal protection unless very deep. SS Sturmbannführer Joachim Paper, commanding the spearhead Kampfgruppe, reported that American artillery was inflicting unprecedented casualties. His combat reports, captured later, described shells that seemed to deliberately burst overhead with mechanical precision. Traditional small unit tactics, dispersion and immediate cover, provided little protection. The advancing units, trained to press through conventional artillery barrages, found themselves unable to maneuver effectively. The 285th Field Artillery Observation Battalion, operating forward with radar units, directed proximity-fused fire missions with devastating accuracy. German assembly areas, identified by radar and aerial reconnaissance, were engaged with time-on-target missions using VT ammunition. The combination of synchronized impact and airburst effects created casualty rates exceeding 30% in targeted areas, levels that rendered units combat ineffective within minutes. At Krinkelt-Rocherath, where elements of the 12th SS Panzer Division attempted to break through American positions on December 17–19, proximity-fused artillery played a decisive role. The 99th Infantry Division's supporting artillery engaged German armour and infantry with VT rounds. Tanks, normally difficult targets for artillery, found their exposed crew members vulnerable to overhead bursts. Infantry following the armour advance were scythed down by fragments they couldn't seek cover from. The effectiveness extended to indirect effects. German medical services, attempting to evacuate wounded from forward areas, found their aid stations targeted with proximity-fused fire. The shells, bursting overhead, penetrated tent structures and inflicted casualties on medical personnel and wounded alike. The systematic degradation of German medical capabilities contributed to declining morale, as soldiers realized that even evacuation to aid stations offered limited safety. General Major Walter Denkert, commanding the 3rd Panzergrenadier Division, included in his after-action report, "American artillery employment has demonstrated technical superiority that renders conventional countermeasures ineffective. Shells burst with consistent precision at heights that maximize casualties regardless of protective measures. Casualties among assault infantry approach 40% in areas subjected to concentrated fire. Recommend urgent tactical doctrine revision." The proximity fuse's impact on German artillery operations was multifaceted and cumulative. Direct casualties among gun crews were severe but represented only the immediate effect. The secondary consequences proved equally devastating. German artillery batteries in the Ardennes operated under constant threat of proximity-fused counter-battery fire. This threat forced tactical adjustments that degraded overall effectiveness. Crews dispersed farther from weapons, slowing response time. Batteries remained in positions for shorter durations, reducing the sustained fire rates essential for supporting infantry assaults. Communication security became paramount, limiting coordination between batteries. The psychological impact was more insidious. German artillerymen, traditionally confident in their technical superiority and professional competence, found themselves outmatched by American technology. The realization that enemy shells could reliably detonate at optimal height without human intervention suggested a level of technical sophistication that German industry, by late 1944, clearly couldn't match. Lieutenant Otto Riemer, commanding a battery in the 18th Volksgrenadier Division, wrote in a letter intercepted by Allied intelligence, "We fire our guns knowing that American response will be immediate and devastating. The shells burst overhead with mechanical precision. Half our battery has been replaced with untrained replacements. The new men last days before they too are casualties. We are being systematically destroyed not by enemy soldiers but by enemy technology." The casualty rates among German artillery crews during the Ardennes offensive significantly exceeded historical norms. Conventional artillery duels typically produced crew casualties in the range of 5 to 10% monthly. During December 1944 and January 1945 inches, the Ardennes, German artillery units reported casualties exceeding 30% for the period, with most losses attributed to American counter-battery fire. These losses degraded German artillery effectiveness in ways that compounded over time. Experienced gun crews, particularly the Unteroffizier who served as gun captains and aimed the weapons, were irreplaceable. Replacement personnel, often drawn from infantry units or hastily trained recruits, lacked the expertise necessary for effective fire missions. Accuracy degraded. Fire discipline suffered. Coordination between batteries became more difficult. The American doctrine of targeting artillery crews rather than weapons proved strategically sound. A destroyed gun could be replaced from depots or captured stocks. An experienced gun crew, trained through years of service, could not be replaced within relevant timeframes. By systematically inflicting crew casualties through proximity-focused counter-battery fire, American forces degraded German artillery effectiveness more thoroughly than any amount of direct weapon destruction could achieve. German attempts to understand and counter proximity fuses revealed a technological and industrial gap that had become unbridgeable by late 1944. Captured fuses were sent to Wehrmacht testing facilities for analysis. The reports that resulted documented sophisticated miniature electronics that German industry couldn't replicate, even if given detailed plans. The Waffenamt report on captured American proximity fuses, dated February 1945, concluded, "The device employs miniature vacuum tube technology of extreme sophistication. The tubes survive firing acceleration through unknown manufacturing techniques. The radio transmission system operates reliably despite severe environmental conditions. The power supply activation system is elegant and reliable." Assessment. German electronics industry cannot produce equivalent devices with current manufacturing capabilities. Recommend investigation of alternative approaches. Those alternative approaches never materialized. German industry, by early 1945, struggled to produce conventional munitions in adequate quantities. The dispersed manufacturing necessitated by Allied bombing, the shortages of critical materials, the reliance on slave labor with its inherent quality control issues, all precluded development of complex new weapon systems. The industrial requirements for proximity fuse production illuminated the gap between American and German manufacturing capabilities. Each fuse required precision-manufactured vacuum tubes built to survive 20,000 G acceleration. American industry produced these by the millions through automated production lines with rigorous quality control. German industry, even at its 1,942 peak, lacked the manufacturing precision and quality control necessary for such production. The battery system alone demonstrated the gap. The proximity fuse was powered by a battery activated by firing setback forces. The battery had to activate instantly, provide stable power throughout the shell's flight, function across extreme temperature ranges, and cost little enough for single-use expenditure. American battery manufacturers solved these requirements through advanced chemistry and manufacturing techniques that German industry couldn't replicate. More fundamentally, proximity fuses represented a systems engineering approach that was characteristically American. The device integrated vacuum tube electronics, radio transmission, power generation, mechanical sensors, and explosive initiators into a package smaller than a hand, designed to function reliably as an expendable munition. This integration required collaboration between electronics firms, chemical companies, explosive manufacturers, and military planners, all coordinated through systematic project management. German weapons development, by contrast, remained largely stovepiped, with individual organizations pursuing technologies without the comprehensive integration that characterized American programs. The Ministry of Armaments and War Production oversaw weapons manufacture, but lacked the systematic coordination that characterized American war production. German forces attempted various tactical adaptations to survive in a proximity-fused environment. None proved consistently effective, but the attempts revealed the systematic pressure that proximity fuses created across German tactical doctrine. Artillery batteries increased dispersion, spreading individual guns 100 to 200 meters apart rather than the traditional 50-meter spacing. This reduced casualties from individual salvos but complicated battery control and slowed fire missions. Fire direction became more difficult when guns were separated by distances that required field telephones or radio rather than voice commands. Infantry units attempted to dig deeper foxholes and improve overhead cover. Positions that might have been adequate against conventional artillery required reinforcement. The fragments from overhead bursts struck at steep angles, penetrating into standard slit trenches. Effective protection required either very deep positions or substantial overhead cover, both of which were difficult to construct in frozen ground with limited engineering support. German forces attempted to increase movement and reduce static positioning. Units that remained stationary presented targets for proximity-focused missions. Constant movement imposed severe logistical burdens and exhausted troops already stressed by winter conditions and limited supplies. The 6th SS Mountain Division, defending in the Ardennes, implemented dispersed positioning with constant movement. Company-sized units occupied positions for no more than 24 hours before displacing. Foxholes were dug deeper, to 3 meters when ground conditions permitted. These adaptations reduced casualties from American proximity-focused fire, but also reduced the division's combat effectiveness through exhaustion and degraded cohesion. General Major Siegfried von Waldenberg, commanding the 116th Panzer Division, reported, "Adaptation to American proximity shells requires measures that degrade our own operational tempo. Increased dispersion reduces concentration of force. Improved fortifications require engineering support we lack. Constant movement exhausts troops and strains logistics. We are forced to choose between casualties from American artillery or degraded effectiveness from protective measures." The adaptations represented a form of strategic defeat, even when tactically successful. German forces that dispersed to survive proximity-focused fire became less effective in offensive operations. Infantry that spent hours digging deeper positions had less time for training and rest. Artillery batteries that displaced constantly after firing provided less sustained support for maneuver forces. German officers who had served on the Eastern Front provided the most pointed assessments of proximity fuses' effectiveness. Soviet artillery, though vastly more numerous than American, had relied primarily on overwhelming volume rather than technical sophistication. A soldier who survived one Soviet barrage through luck or proper technique could reasonably expect to survive the next. Proximity-focused American artillery eliminated the randomness. Every shell functioned as intended. Every burst occurred at optimal height. Survival became primarily a matter of not being targeted rather than taking proper protective action. This systematic reliability proved more psychologically devastating than even the heaviest Soviet bombardments. Major Kurt Meyer, an artillery officer who had served 2 years on the Eastern Front before transfer to the West, wrote in his diary, "Soviet artillery could be survived through experience and discipline. Their barrages, though terrible in volume, were survivable by trained troops. American proximity shells remove the element of survival through skill. The shells function with mechanical perfection. There is no exploitation of enemy error because there is no error. This is warfare by industrial process rather than human action." The contrast extended to counter-battery operations. Soviet counter-battery fire, while often intense, could be avoided through rapid displacement and camouflage. Soviet fire control was slower, allowing German batteries time to fire and displace. American radar-directed counter-battery fire, employing proximity fuses, arrived within minutes of a battery revealing itself, and the proximity-focused shells created casualty patterns that made displacement less protective. German artillery officers recognized that they faced not just superior numbers but superior systems. The combination of American radar surveillance, rapid fire direction, reliable communications, and proximity-focused ammunition created a comprehensive superiority that no tactical adjustment could overcome. Proximity fuses represented one component of American artillery superiority, but one that particularly impressed and demoralized German forces. The devices embodied several characteristics that defined American military capability in 1944 to 45. First was technical sophistication. German forces by late war had grown accustomed to American technical superiority in vehicles, aircraft, and communications. The proximity fuse demonstrated that this superiority extended to artillery ammunition, traditionally an area where Germany had maintained rough parity. Second was systematic reliability. The fuses worked consistently. They functioned in extreme cold, in rain, in mud. They survived rough handling during logistics. Failure rates remained negligible. This reliability contrasted sharply with German experience of their own ammunition, which showed increasing variability as quality control degraded under wartime pressures. Third was scale of production. American forces employed proximity fuzzes freely, even profligately by German standards. Fire missions that might warrant 10 conventional rounds would receive 10 proximity-fuzzed rounds. The industrial capacity to produce complex electronic devices in quantities sufficient for routine combat use suggested resource depths that Germany simply couldn't match. The security surrounding proximity fuzzes added a psychological dimension. German intelligence knew the devices existed, but couldn't fully analyze them due to the difficulty of obtaining intact examples. The few recovered duds revealed technology that couldn't be replicated. This suggested that the Americans possessed other weapons whose existence remained secret, an impression that proved strategically valuable even beyond the fuzzes themselves. General der Artillerie Walter Warlimont, writing after the war, assessed, "The American proximity fuse represented not merely a technical advance, but a demonstration of comprehensive superiority. The device itself was sophisticated. The scale of production was staggering. The security was absolute. The employment was systematic." German forces faced not just a new weapon, but evidence of an industrial and organizational capability that we couldn't match. The proximity fuse's value in defensive operations became apparent as German forces retreated across Western Europe in early 1945. American units, often outnumbered locally by German counterattacks, could employ proximity-fused artillery to generate defensive firepower that multiplied their effective strength. At Colmar in January 1945, where the 3rd Infantry Division faced determined German resistance from the 19th Army, proximity-fused artillery proved essential. German counterattacks, attempting to dislodge American positions, were engaged with VT-fused fire missions that inflicted heavy casualties on assault infantry while they were still in approach formations. The consistency of effects allowed American fire direction centers to plan defensive fires with confidence in their results. A battalion fire mission, employing proximity fuses, could be expected to inflict 30 to 40% casualties in targeted infantry formations, levels that typically broke up assaults before they reached American positions. General Lieutenant Hans von Obstfelder, commanding the First Army during the final Rhine battles, reported, "American defensive artillery, employing overhead burst ammunition, creates barrier fires that assault troops cannot penetrate. Our infantry, attempting to close with American positions, are decimated at 300 to 500 meters from their objectives. The precision and lethality of these fires requires concentration ratios of 3 to 1 or greater to achieve breakthrough, force ratios we can no longer generate. The defensive value extended to protecting logistics and rear areas. German attempts to disrupt American supply lines through artillery fire or air-mobile operations were countered with proximity-fused fire. Transport columns, normally difficult targets for artillery, could be engaged effectively with airburst ammunition that struck exposed drivers and loads. As Allied forces drove into Germany in early 1945, proximity fuses became standard ammunition for most fire missions. The scale of employment revealed the depth of American industrial production. Monthly proximity fuse production exceeded 2 million units by March 1945, more than Germany's total artillery shell production of all types. The Rhine crossings in March 1945 demonstrated proximity fuses at maximum effectiveness. At Remagen, where American forces secured the Ludendorff Bridge intact, proximity-fused artillery devastated German counterattacks attempting to destroy the bridgehead. The 78th Infantry Division's supporting artillery fired over 12,000 proximity-fused rounds during the first 5 days of the bridgehead operation. At the Oppenheim crossing on March 22 to 23, Patton's Third Army employed proximity fuses as standard ammunition for the preparatory bombardment. The systematic airburst fire suppressed German defenders so effectively that the initial assault waves crossed with negligible casualties, despite the technically difficult river crossing operation. German forces, by this point, had largely abandoned attempts to counter proximity-fused fire through tactical adaptations. The cumulative effects of 5 months of exposure to VT ammunition, combined with broader strategic collapse, had created a fatalistic acceptance. Proximity fuses were simply one more manifestation of Allied material superiority that couldn't be overcome. General Major Rudolf von Gersdorf, serving as Chief of Staff to the 7th Army, assessed in March 1945. American proximity-fused ammunition represents perfection of artillery effectiveness through industrial means. We possess neither the technology to replicate these devices nor the industrial capacity to produce them in militarily relevant quantities. This single weapon system, combined with American superiority in radar, communications, and logistics, creates artillery effectiveness that renders our defensive operations nearly impossible. The German experience with American proximity fuses influenced post-war military development across NATO and Warsaw Pact forces. The revolutionary nature of the technology was recognized universally. The ability to reliably detonate artillery shells at optimal burst height without human calculation represented a fundamental advance in artillery effectiveness. The Israeli Defense Forces, established in 1948, sought proximity fuse technology immediately as a force multiplier for their limited artillery assets. The French Army revised its artillery doctrine specifically to incorporate VT ammunition. The British Royal Artillery, despite having been briefed on the technology during the war, accelerated its own development programs after seeing combat effectiveness in 1944–45. The Soviet Union, denied access to proximity fuse technology during the war, launched extensive development programs immediately after capturing German intelligence assessments and occasional physical examples. Soviet post-war artillery doctrine assumed that future conflicts would involve mutual use of VT-fused ammunition, requiring tactical adaptations that German forces had attempted unsuccessfully. The Bundeswehr, reconstituted in 1955, incorporated lessons learned from Wehrmacht experience with American proximity fuses. German artillery doctrine emphasized dispersion, rapid displacement, and improved survivability measures, all responses to the devastation that VT ammunition had inflicted a decade earlier. The technological principles pioneered in the VT fuse influenced broader military electronics development. The ruggedized vacuum tubes developed for proximity fuses advanced the state of military electronics generally. The systems engineering approach that integrated electronics, mechanical components, and explosives in a single package became characteristic of Cold War weapons development. Modern artillery fuzz, employing microprocessors and digital signal processing rather than vacuum tubes and analog circuitry, trace their conceptual lineage directly to the World War II proximity fuse. The principle remains identical. Autonomous sensors determine optimal detonation point without human intervention, maximizing effectiveness through consistency and reliability. The German experience with American proximity fuses represents a case study in technological surprise and industrial superiority. German artillery crews, among the most professional and capable in the world, found themselves systematically outmatched not by superior gunnery but by superior technology applied at industrial scale. The VT fuse didn't change warfare's fundamental nature, but it changed the arithmetic of artillery effectiveness. A weapon system that had achieved incremental improvements over centuries suddenly achieved a multiplicative increase in lethality. German forces adapted as best they could but found themselves facing a technological challenge that admitted no tactical solution. What German artillery crews never imagined, what they couldn't comprehend even after months of exposure, was that American shells could reliably detonate 30 feet above their positions with mechanical precision, that industrial processes could produce millions of sophisticated electronic devices and treat them as expendable munitions. That quality, control could ensure nearly 100% functionality in combat conditions. The thunder that arrived from above, detonating with perfect timing at perfect heights, announced more than American technical prowess. It demonstrated the transformation of warfare into industrial process, where victory belonged to those who could best apply technological sophistication at massive scale. German soldiers who survived proximity-fused artillery lived with the knowledge that they had faced weapons against which courage and skill provided inadequate defense. The fragments that rained down from precisely timed overhead bursts killed professionals and conscripts with equal efficiency, making no distinction between veterans of 5 years combat and replacements of 5 days service. In the evolution of military technology, few weapons achieved such immediate and sustained impact as the proximity fuse. German forces, experiencing its effects for the first time in December 1944, found themselves confronting not just a new weapon, but a new era in warfare, where technological and industrial superiority could trump tactical skill and operational art. The lesson was harsh and absolute. In industrial warfare, systems defeat soldiers, production capacity trumps tactical innovation, and perfectly timed automatic detonation conquers all. Up next, we have 2 more incredible stories that are waiting for you. Just click the image you want to watch and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.